So for the 9 of you that are here right now, any questions that you have, there's a Q&A thing on the side. You can just go ahead then send those to all panelists so that we make sure we get to your question and that the panelist that's presenting doesn't accidentally miss your question. So we'll pass it off to Dr. Bart now.
All right, hi everyone. So I'm here today to talk to you a little bit about the OP. Obviously, I'm a professor in the Inorganic division, so keep in mind that I'm going to be giving you some general tips, which are good for any division, and then probably some more that are a little bit more division specific. So just to be aware of that. So I know Anna sent out the OP help tips. So let's start with the do half of that. So things that would be very good to do for your OP. So the first thing you want to do is choose a topic that interests and excites you. So as you know, you're supposed to be writing an original proposal about an area of chemistry that hasn't been explored. And the easiest way to kind of get into it is to do something that you think is really exciting. So if you have a topic that you think is maybe just okay, you might want to think about switching it, because the more excited you are about the topic, the more interested you're going to be to work on it. And overall, the better your document's going to come out and the better your discussion is going to be at your exam. So make sure that you pick something that really interests and excites you. So as I mentioned, like some of these tips are going to be a little bit divisionalized. So you definitely want to ask your research advisor, or you can check the grad student handbook to learn about divisional guidelines. So I know, like, for instance, I think in biochem, they do like an NIH format or something. In inorganic, we don't have a specific format that we use. You know, so I usually tell students about 10 to 15 pages. Double spaced, because nobody wants to read like a hugely long document. So, but if you're in other divisions, I would definitely recommend that you ask your advisor or check the graduate student handbook. So going back to choosing an idea that interests and excites you, you want to come up with a couple of ideas and spend time researching them. And then pick the idea that you think would be the best project, right? So don't just pick one idea and, you know, kind of like put your blinders on and say, I'm definitely doing this. You want to research a few ideas, because once you learn a little bit more about them, you'll have a better idea of what's going to be more amenable to the report and the exam format. You know, if you come up with other ideas that you really like, but you think they're going to be hard or not amenable to this format, certainly save them, because you could definitely do them at another point in your career. But remember, what you're doing here is you're trying to pass an exam. So you definitely want to do something that is amenable to this format. Please use figures to make your report interesting and effective. So a lot of times the figure will convey something that will be difficult to say. So you want to make sure that you use figures. It's fine to take from the primary literature as long as you reference them appropriately. This one should go without saying, but I've seen a lot of OPs, and this is not always the case. So you want to make sure you actually propose something. When you write your report, it's going to be very important that you think about, like, if you are actually going to do it, what you would do in lab. Like, think about actual experiments and lines that you would study. You know, I have been in some OPs that don't actually propose anything. You know, they're more like literature reviews sometimes. So you want to make sure that not only do you propose something, but you make it very clear to your committee what you're proposing. So use lots of headings, use bold fonts, use sections. You want that actual proposed work to be very, very clear. Definitely seek help from older graduate students and other professors. So as you know, you're not really supposed to be talking to your own PI about your topic, about your presentation, but there's so many experts around in so many different things. Please make use of these resources. Whether they be graduate students, postdocs, other professors, there's nothing that says that you can't go talk to these other people to develop your ideas. So please make sure that you're using the resources around you to help develop your ideas. Please ask someone to proofread your report for you, please. Make a talk that's engaging and recognizable to your report. So you don't want to stray too far from your report in your talk, because your committee is going to have read that. When they come into the room, they're going to have some idea what you're talking about. So you don't want to just go and do something completely different for your talk. You want to make it recognizable. But also remember that this is your opportunity to teach us about something. So you want to make a talk that's engaging, a talk that is going to allow us to ask you questions. So that's really important. You don't want us to be like bored or not paying attention during your talk. It's also going to be very important that you do practice your talk in front of a group of people. Now, I know that because of COVID, that is a little bit different. So you're going to want to practice it over Zoom or WebEx or something, but please practice it to a group of people that can give you feedback, because the feedback that you get will really help you in improving your talk. And if you gather a good group of people to listen to your talk, I've heard a lot of people say that their practice was harder than their actual exam. So if you gather the right people, you'll be very prepared for your exam. And, you know, in pre-COVID, dressing professionally from your presentation was important, but now all I'll say is wear a nice shirt. All right, let's switch over to the don't tips. Okay, so these are also things that you really want to keep in mind. So make sure that if you're taking excerpts, quotes, figures, tables, make sure that you reference them both in the talk and in your document, okay? You don't want to be just ripping from things and not referencing it, because your committee will definitely call you out for that. Also, don't fabricate data to show what the outcome of your proposal would be if you actually did it. So as researchers, we're not supposed to be encouraging our students to fabricate data. So don't do something like that. But what is a good idea to do is to say, if I were to do this, this is what I would be looking for, or these are the trends I would expect to see, or I would expect data that looks like this or something. But don't actually fabricate data and graph it and put it in your report. That's really not a good idea. We want to know that you can think on your feet and you can think about your project, but we don't want you to spend your time making stuff up. Don't make your report super long. So certainly one of the things we're going to be looking at in your OP report is your ability to convey an idea concisely. So if it's a lot of pages, you know, if it's significantly more than 10 to 15 pages, we're going to think that, you know, probably we're going to think it's like repetitive and wordy and stuff like that. So you want to demonstrate to your committee that you can write concisely, because that's certainly an important professional skill. And don't start your report the week before it's due. That's not going to give you enough time to write what you need to write, to think it over, to ask experts. Like, there's just not enough time. So make sure that you give yourself plenty of time. And don't make your talk really long either. Again, this is a divisional thing, but you want to be able to present your idea concisely, maybe in around 30 minutes, giving a lot of time for discussion and questions. To me, the most successful OP exams are when we have a nice scientific discussion with the student and the student is comfortable, you know, they're not super stressed. If you make your talk really long, you're going to be so worried about getting through all your slides and you might not get through them all. So make your talk concise so that you can get through the whole thing and you can discuss all the important points. Don't think that you don't need to practice. Everyone needs to practice. You know, I've been here, this is my 13th year. I still practice my talk sometimes. So make sure that you practice your talk, as I mentioned, in front of a group of people that'll really ask you good questions and challenge you, because I promise you will feel so much better walking into that room if you've practiced. Don't dress like you rolled out of bed. Again, wear a nice shirt. Think you have to do it by yourself and you can't get input from others. So of course you can't do it by yourself. Like none of your advisors write proposals by ourselves. You know, we're always asking our colleagues, asking other people in the field, asking collaborators. You know, nobody does this by themselves. So please make sure that you get input from others, whether it be your friends, other students, other professors, things like that. And please don't disregard the divisional guidelines. So as I said, it is a little bit different per division, but make sure you're aware of those going in so that you don't waste time or you don't have to do things over. So to me, those are some of the key points, but the most important are make sure that you propose something and make sure you make your report concise and make sure that you make your presentation concise as well, and practice, practice, practice. Are we doing questions now?
Yeah.
Okay.
So if you have any questions, you can type them in the Q&A box and send them to all panelists.
Yeah, I'd be happy to answer any questions if people have any general questions or more specific towards the inorganic division.
I guess oh, okay. Can data be simulated?
That's kind of an interesting one. I think that you can simulate the data as long as you make it clear that the data is in fact simulated.
Can the entire OP be on Zoom or WebEx, or do we have to do it in a large conference room? I think that's in the general policies. Sorry, I'm just going to take this one.
Okay.
That I think the department is having everything online this semester.
Yes, that's correct.
Yeah. And so if you see the attached documents that I sent in the email twice today, the general policies and procedures was reviewed by Jenna Lee. And then a general question, how do you recommend getting started finding a topic or idea?
Okay, great. So for me, finding a topic or idea, I spend a lot of time reading the literature. So I read maybe some papers that like I just think are interesting and maybe they're not super related. And as I do more and more reading, a lot of times I find that I can get some neat research ideas by either maybe combining two of those papers, combining them into combining the two ideas into one, or I'll be reading a lot about an area and think, oh, I wonder if anyone's ever tried this. And then I'll go look that up to see if they've done that. And if they have, maybe I can tweak it a little bit to kind of cover an area that they haven't covered. But to me, certainly, finding a topic or idea starts with reading the literature, but reading things that like I just think sound cool. You know, so not necessarily like constraining myself to like a specific area.
Jennifer wants to know if there are any divisional guidelines for inorganic students, or if you could explain a little bit more about that.
So in terms of inorganic students, what I usually tell my students is that we don't have a specific format for the paper, but generally 10 to 15 pages double space. In the inorganic division, most of those exams usually go about an hour or so. So like I said, maybe like 20 slides that you can go over and have like a good discussion with your faculty members. In the inorganic division, generally the topic should not be related to your research. I know that is not the rule for all divisions, but in inorganic, we want to see you go outside of your typical research area and so choose something else. So I'd say those are probably the most important divisional guidelines we have.
Okay, we'll end with that question, and then if anybody has any general questions, we can answer them at the end, or you can ask any of the other professors presenting, and we'll let Dr. Bart go and go to her next meeting. Thank you so much.
Thank you. Yeah, if you have any additional questions, feel free to email me and I can either answer them or we could have like a smaller Zoom meeting or something. All right, thank you. Good luck.
So now we'll move on to Professor Wei with organic chemistry.
Hi, everyone. So first of all, I want to just echo everything that Dr. Bart said in terms of the general approach to doing the OP. She really nailed it. Maybe there's only one point I want to emphasize especially, and that is to be sure that when you're preparing the OP and also defending your OP, that you identify the key original idea or the question that you want to answer. Okay, so this should always be up in your mind. Every day that you're working on OP, you should be repeating yourself. What is the idea or main question that I'm trying to address through a research proposal? Okay, so having said that, let's get started on some more specific tips. So I'm representing the organic division, and we don't have division-specific guidelines, but there are categories that the majority of students from organic division will choose. And so I'll go through each one of these in turn and try to keep us on track. I'll end at 1:30. But about approximately a third of the students will choose some sort of synthesis or target-oriented project or methodology, catalysis. And so there are some tips and tricks and do's and don'ts for that. Another group will choose something related to chemical biology or drug discovery. And that has its own pluses and minuses. And the third one is designing some sort of material or functional structure, a molecular design type project. So in all of these, what they share in common is that in your OP, you want to design an argument that helps you establish a proof of concept. And you want to be aware of the potential pitfalls, right? If you, in the course of your preparations, you find something that maybe is a little dicey, you don't have to necessarily bring it out, but you want to be prepared to answer questions, because if you found it, it's very likely that your OP committee member, one of them, will point it out as well. Okay, and so considering the pitfalls and alternative plans in case your best ideas don't go forward, that's all part of the preparation. Okay, so I'll go to the first slide. So when it comes to synthesis, you definitely want to know your mechanisms. Okay, so if you're putting together molecules, so in addition to the key bond forming step or ring forming step, all the smaller steps in between are important. Protecting group chemistry is an amazingly important yet overlooked part of doing synthesis. Knowing the mechanisms of how protecting groups come on and off, knowing the compatibility between protecting groups, that's something you should really review and include as part of your basic knowledge. Okay, next on. Very often as you start talking about your proposal and defending it, it gets down to the basics. pKa comes up actually quite often. And so you want to keep in your mind what's clear about relative pKa. Memorizing the numbers isn't as important as knowing what's more acidic or basic than something else, right? And so solvents, conjugate acid, if you're doing a reaction in pyridine, that's very different than doing it in DMF, which is again very different from doing it in methylene chloride. And so the relative acidity of your solvents or conjugate acid to those solvents is something that's worth reviewing. The same thing goes for Lewis acids. And so a lot of things behave as Lewis acid and bases. What are those compatible with? Are they compatible with the solvent and the functional groups, right? That's a very basic part of designing your synthesis. Okay, is there another part to that one? Okay, so when it comes to the key step, that's usually where your committee would like to ask questions. In order to say that this works, you have to be able to establish the structure. Okay, and so of course this goes back to things like spectroscopic analysis. Crystallography is always a backdrop, but you don't always get crystals, and so on occasion, or maybe more than on occasion, someone will ask you, how do you know you got the structure that you propose? And so thinking about how to get to that structure and how to prove it is important. Nowadays, there was a question earlier about simulating things, computation for knowing whether a reaction goes forward or a structure is stable. That's also becoming increasingly uh, uh, frequent in its use. I would say that you can do it, but don't rely too much on it. It's definitely not the panacea to any of your things. Just because something appears to work nicely by your first attempt a calculation doesn't mean that it's going to work in the flask. So it's a piece of supporting information. It helps, but it's not something that you should use as a hard fact. Okay, it's just simply to show that you're on track with your idea if you choose to use computation. You're not required to, of course, but it is becoming increasingly popular. Okay, and lastly, just as a rule of thumb, uh, before going into your OP, you should probably review your basic core course notes from organic chemistry. 651 for sure. If you're doing synthesis, 652. Okay, if your OP committee member was a former instructor of yours, definitely review the material from his class. Okay, so that's good for synthesis. Let's move on to the next topic. So with chemical biology, here the emphasis on synthesis is not as strong. You still need to know how to make your molecule, so all the comments from before do apply. But what becomes increasingly important in something like chemical biology OP is to know your assays, right? So you want to establish some kind of inhibition constant or IC50. If you're doing some kind of microbiology experiment, MIC50, be sure to that you know the basis, that you can explain how the assay works. Okay, and also equally important, be sure that you add controls in your written OP. Okay, so you want to prove these things. How do you know what is it relative to? So adding controls is very important. Not necessarily so difficult, but you have to think about it. You always want to be thorough in your background research. I think this goes without saying. And the hypothesis has to be clearly defined. So this goes back to what Dr. Bart was saying about, doing a literature review versus an OP, right? You can get kind of stuck in the weeds and do a lot of literature review and then never really formulate the question. So you want to make sure you identify that original question, but you also need to do enough background research to make sure that the question hasn't really been addressed. Okay, if part of your idea has already been tested, that's okay, right? But you want to clearly establish what part has not been tested and what you set out to prove. So in line with that, the background, you can be familiar with your biological system. That's always an important thing to do. And if you are targeting a pathway, you should be aware what kind of things are upstream or downstream of this and how they're related to expression. So no biological process acts in a vacuum. You want to know if you turn it on and off, what other things get turned on and off, and also what things are upstream of it so that it's there for you to explore. And very importantly, don't be too broad in your scope. You really want to be specific. Don't say that you're going to cure cancer. I know no one will say that, but you want to target something rather specific, right? There has to be an endpoint that allows you to say yes or no, right? That's really the hallmark of a successful project of any sort. Okay, and so getting to know what steps are necessary. Usually, if you're designing a drug, uh, uh, the realistic thing to do is that you're shooting for preclinical application, right? If you're going to propose to test in clinical, in a clinical phase trial, you're probably going too far unless you're already starting from something that's already been proven. So if you're creating something exploratory, what you're really trying to do is you're trying to hit preclinical benefits as opposed to trying to test them in human subjects. Okay, so details on that I'm happy to talk about if anyone wants to go in that direction. Okay, so the last area, and I think in my opinion, maybe the most fun and diverse area is designing molecules or materials that do something. Okay, and again, just like in the drug discovery type of approaches, do an extensive reading on the background. Be very clear what is already known about the system, and then define what is it that you want to do. And the best thing to do is always to have some sort of quantifiable outcome. Okay, so finding a absolutely brand new function is pretty hard to do these days, but being able to improve on a function or combine functions, certainly that's possible. So make sure it's very clear what your goals are. Okay. The function itself, you'll have to explain what advantage that your particular system has over others, right? So again, we're going to assume that the area of interest that you're looking into has already been pretty heavily researched. Okay, so we want to know why what you're doing is worth doing. What's its value? Okay, for just like molecules, you need to characterize materials, but this goes beyond chemical characterization. More often than not, there's some kind of physical property that you'll need to address, especially related to your function. So whether it's optical or magnetic or mechanical, be sure to be sure to be knowledgeable about that method of characterization. Okay, and if you're asked, it's a very popular OP question. How does that work? Be sure you can answer how that characterization tool works. Okay, is it a good match for studying what you want to what you're looking at? Okay, and everything has limits. Be sure to tell people what the limits are. Okay, the modeling, again, going back, it's a similar idea as synthesis. It's getting commonly popular to start using models, computational models. You can use them to support your hypotheses, but really the focus should be on the experimental systems and what sort of analysis and testing that you're going to do. Okay, for materials research, it's very important not to be vague. Okay? You really need a well-defined outcome. So being quantitative is an important aspect for this. Okay. All right. So I think that summarizes the slides that I have. Okay. I'm very happy to answer any questions that you may have.
Once again, for a lot of people who just joined, make sure when you send a question that you send it to all panelists so that we can see them. Yeah, we'll give a second for you guys to type them up.
While we're waiting for a question, I just want to give a quick anecdote about a cautionary tale for some OPs. So this really comes down on the topic of being able to define what your outcomes are. Many years ago, a student, a really intelligent student, tried to propose something that would make a system safer. I love safety, as you probably know, but defining what is safer or safe was really difficult. And I think in the end, that proved to be the Achilles heel to his approach. So when you want to make something better, right, quantifying why it's better is super important. Okay.
Okay, if you are proposing a mechanism, what advice do you have to avoid certain pitfalls?
Well, I'm not sure what specific advice I can offer regarding mechanism. So if it's basic organic, if it's classic organic chemistry mechanism, arrow pushing, right? Single arrow versus double-headed arrows, right? Whether using 2 electrons or 1 electron is something that you'll definitely want to keep track of. Everyone knows that that arrows should leave from the electron-rich species, a lone pair or nucleophile, and go toward H plus or the electrophile. So don't screw up your arrows. Radical-based mechanisms are always a little bit trickier because you're dealing with 1 electron at a time. I would just simply say that having a strong basis in arrow pushing mechanism is probably the most important aspect to it. After that, it really gets down to the details. For transition metal based catalysis, those kind of mechanisms, I think people would expect you to know the basics again. Oxidative addition, reductive elimination, migratory insertion. Photochemistry, also there are some basics to go with that. So you don't need to know every single mechanism for every type of reaction, But for the ones that are important in the chemistry you're proposing, they're definitely worth a review.
Any other questions? So far, there was only that one, so.
Okay. So like Dr. Bart, I'll be happy to answer questions that come up later offline. So good luck to everyone.
Okay, I guess we'll just move forward then. And if anybody has any general questions, you can go ahead and type them and we'll answer when we get to. So thank you so much. And we'll move on to Professor Wasserman now for physical chemistry.
Hello? Can you hear me okay? Well, thank you. Hi, everyone. It's nice to see you, at least some of you, and to see your names here on my right-hand side of the screen. I wish this could be in person. Hopefully, next time. Okay, so I have here prepared a couple slides. Now, thank you. Yes, so I see that, Anna, you are... okay, that's good. Yes, that helps me also. I prepared just 2 slides. The first one is about what is expected for the PChem division's OP. And the second slide is about some hopefully helpful preparation tips. So here we start with what is expected. And I added 2 notes in gray. So I'll read along. So let's do that. Let's just read along. And if you want to stop me, feel free, or then we can address questions at the end. First note, specific expectations may vary among faculty. Such is life. And that's part of the challenge, right? In an ideal world, everyone on the faculty would agree on what is expected from you. But the reality is that different people have somewhat different expectations. And that's just how it is. By the way, it's similar when you are submitting a real proposal for funding at the NSF, for example. You'll get a committee to review the proposal, and some people will have some expectations, others will have different expectations, and so that's how it is. However, note number 2 says that general expectations are the same for all. The OP should be original, interesting, and generally correct. From the written document and the oral presentation, it should be clear that you, and here I listed 3 points. First, have studied well an area not directly linked to your PhD project, and can clearly identify and state one concrete problem that you are proposing to solve. So it sounds easy, maybe, or obvious, but the truth is that often we don't see this. We get to the end of the OP and the committee is wondering, well, what was the one concrete problem that the student was proposing to solve? So it's really important to have this clearly. You can do 2 problems, but I think that's already overambitious. 1 concrete problem to solve. 2, you have studied and understood the fundamental physical chemistry principles that provide appropriate background and context for your proposal. Every problem that you choose for your OP will have some underlying principle, physical chemistry principle, if you're in the PChem division, that will be important as background. And that fundamental principle needs to be well understood when you go to do your OP. 3, it should be clear that you have given some serious thought to how you would attempt to solve or approach the problem and what the main challenges are. We're not expecting a complete solution to any problem. After all, it's a proposal, it's not a full solution, but it should be clear what the approach is. and what the main challenges are. Yeah, perfect. Yes, a few preparation tips. To make it interesting, you need to be genuinely interested. I think this is really key. How are you going to convince a committee that something is interesting if you don't find it interesting? It's pretty much impossible. You have to try to convey your excitement to the committee. How do you do that? I'm not sure. Here in parentheses, I wrote down try to pin down somehow why you chose the topic, why you find it interesting, and explain this as best as you can. Be ready to explain the meaning of every word, plot, or comment from your written document and slides. If something is not necessary to make your point, don't include it. Yes, it's a common thing that there's a word on your slides and someone asks what's the meaning of this word, and it's really bad if you don't know, because everything that's on the slides or on your written document is assumed to be well understood. So one good advice for doing this is to not put too much. Don't have the slides very crowded. Only have what's essential to what you're saying. Practice, because when practicing, oh, I'm sorry. So you put yourself in the shoes of someone who is listening to your presentation for the first time. Pretend you're a committee member, and you will want to know whether the speaker, that's you, has a clear proposal in mind. Ask yourself whether you know the meaning of everything you're showing on your slides, and strive for clarity. The committee will be impatient to know what your main point is and why it is interesting and important. Different people are different. Some people in the PChem division are very patient and will wait until you get to your main point. I guess I'm one of those who is generally quiet and waiting until you. But other people in the PChem division will be impatient and will jump and say, "Hey, what's your main point? Get to it." And maybe for this, it's important to have one slide, not necessary, but I think it's a good idea to have one slide that clearly states the problem you're proposing to solve and why. This is hard to do. I would say that instead of aiming for perfection, which may lead to nothing, aim for interesting and thoughtful. I've seen cases of really bright, excellent students who want to have a perfect OP, and the problem of that is that the time is so limited to prepare the OP that it's pretty much impossible to have it perfect. And that can become paralyzing for someone who's a perfectionist. Trying to do it perfect is maybe not a good idea. It's better to shoot for interesting and thoughtful than to shoot for perfect. You may have chosen a topic that no one in the room knows anything about. This happens often. And that's fine, but it raises special challenges. The questions will go to the core and to probing the overall logic. It's not a problem to make a few mistakes or to say a few things that are incorrect. The problem is to not recognize this and try to mask misunderstandings with confusion. Yeah, so this happens often. It doesn't work in an OP. It works sometimes in government, apparently, but not in the OP, in PChem. And I think this is all that I brought. You see, I was way under 10 minutes. I read it too fast, maybe. I don't know. It's hard when it's online. I don't have a sense for.
It's okay. Plenty of time for questions.
Okay,
we were a little behind anyway, so it caught us up. Perfect.
Okay.
Yeah. Make sure you put your questions in the Q&A slot, because it doesn't notify me if it's in the chat. Sorry about that.
I've seen a few questions here. I don't know if these are old or new questions.
Those are old.
Okay.
Yeah. Unless you have any that are specifically towards you. Oh, there's 2 new ones. Okay. So, how different can the topic be? Can we work on an idea to solve a problem someone else in the lab has already worked on?
How different from your PhD?
Yeah.
Yes, so this is the answer to this question may be one of those examples where expectations vary between people in the committee. For me, it's perfectly fine to choose a topic that someone else in the group has worked on. If it's not, so anything that's not your specific project for your PhD is fair game. I think most people would agree with this. The idea is to take you out of your comfort zone. That would be your PhD project, but it should still ideally be useful for you. It's something that will be useful for you, and chances are that if it's something related to what someone else in the group is doing, that's going to be useful for you as well. So that would be fine for me, and I think for most people in the PChem division. I see.
A related question, a
Yes.
little higher up, is the question or the principles used to address any PhD project, like specifically yours also. Could you use those principles to address a completely different project for your OP?
The principle used to address the PhD project. And yes, absolutely. It's just, second law of thermodynamics could be an example of the principle. It applies to so many things, and so it applies to your PhD project, but it also applies to any other project you can think of. So again, this is perfectly okay for me. Maybe it's not a bad idea to consult briefly with your other committee members as you are starting to plan for the OP. Just a quick check, an email saying, hey, would this general topic be okay with you? Sufficiently different from my PhD work. I think it's, in fact, a very good thing if you are basing your OP on if your OP is based on the same fundamental principles that you need for your PhD, but it's applied to something different.
This final question, I guess, could be answered by anybody, more particularly Dr. Wei, but if there's a protein that's being made recombinantly in the lab for screening purposes, could their OP be on the biology of this protein?
Yeah, hi. I saw that question, and I was thinking that the biochemistry division might be a better group to be able to answer it. But in general, you don't feel like yes, you can actually make your OP question directed toward a biological issue. There's nothing wrong with that. Again, I think all the comments that were raised before still apply. Please do be aware what the scope of knowledge of your OP members are. So that's about all I can say.
Yeah, I can comment on that very briefly from the biochemistry division that a lot of the points that Dr. Wei already raised about knowing what's in a pathway, what's upstream, what's downstream, knowing the assays that are necessary to characterize a protein or something you synthesize certainly could be part of an OP. The challenge, of course, is in ensuring that those are not necessarily standard characterizations, so that you are still answering a unique question. It's not simply that you have a reagent in hand and the characterization at a very cursory level is what you're trying to present. You still need to be addressing a problem. And I think all of the other PIs have already suggested that in a variety of different ways, but that would be what I would say.
I think this question was more about if the lab is already using a protein, can you do an OP about like the biology of it or using the same protein in a different way?
Oh, I understand now. Yeah, so if it's a protein that's already being used in the lab, I would say that uh, there's no rule against that. Maybe what's better is to consider the trade-off. So whether it's biology, biochemistry, or even synthetic chemistry, the closer your OP idea is to your research, the more heavily your committee will scrutinize you. So there's kind of a, just like in the Olympics, right? There's you get points for performance and points for challenge. The further away your research topic is from your defined expertise, uh, um, the more lenient your judges will be. So if it's a protein that you yourself are not involved in any way, you just happen to know something about it because of discussions with your lab mate, there's nothing wrong with proposing an interesting idea related to that. But if you're working with that protein and you just have another idea for it, uh, just be aware that your committee members, will take for granted that you should really know that stuff well. I think that's the best way of putting it.
Yep. Okay, so I think that was the last question, so we can move forward to biochemistry now with Dr. Lonam.
Excellent. So thank you to the organizers for putting this together. This is a really nice opportunity to better understand how the different divisions are addressing the OP and to give students the opportunity to ask questions. So I think a lot of the broad ideas have already been addressed. So I'll try to point out some of the specific items for biochemistry. As Dr. Bart had already pointed out, we use a pretty specific format, which you can see at the bottom of this slide, which is based loosely on an NIH style grant. But to go briefly over the research plan, you'll notice the first thing that's highlighted in bold is that we really expect this to be hypothesis driven. So overall, the way your research plan is going to be scrutinized by your committee is to try and understand the scope of the project, the techniques that you're suggesting to use, your expected outcomes, as well as your anticipated challenges. And all of this needs to be under a hypothesis, a central question. And this has been highlighted by others as well. And one of the things Dr. Bart said that I think I would amplify is try to do this routinely. So as you read in the literature, or you speak with colleagues, or you speak with friends, think about what questions might still be out there. And then, as Dr. Wasserman just pointed out, think about how to articulate a question. This is actually much more challenging than you might immediately think. That in order to have a concise and clear question, this is something you have to keep practicing. It's a skill you build. So below that, you can see that we think about questions around the novelty of this hypothesis, the significance, and the feasibility. One way to think about this from a problem-solving perspective is try not to be gee whiz, as the way I would say it. So imagine, for example, you've just read a really neat paper on prostate cancer, and you think that the new technologies that have been developed, screening assays, whatever, sound really interesting and could be really important. I wouldn't encourage you to just say, I wonder what the outcome is if I applied this to pancreatic cancer, right? Instead, think, for example, what might another cancer that's driven by hormones, let's say breast cancer, how might the androgenic effects of a paper you've read about prostate cancer imply something about breast cancer, and how could you stage a question around that? So I think it's really important not to be gee whiz. You'll notice that it says organize around why the work is important, what has already been done, what do you intend to do, how is it novel, and what are the actual techniques. So as Dr. Wei pointed out, rarely are you the first person to think about an idea or even a connection between two topics or several technologies. So really make sure that you're thinking very carefully about the question and how you're staging it. And to try and be fair, you do not have to take a giant leap forward in the field. That's not the expectation, but you should be contributing some new knowledge through your proposal. Okay, and you can look at the specific formatting guidelines. You can see about 10 to 12 pages, specific fonts and sizes, but you can look at all of that at your interest. Okay, so as is typical with an NIH style grant, you'll start with a specific aims page. Notice that this is one page shown in bold here. And so really concisely, what an aims page does is it says what, how, and so what. So what is the question? And again, articulate it as clearly and concisely as possible. How will you go about addressing that question? And so what? What is its significance? What is its importance? Again, if you read through this, you'll notice that 2 to 3 specific aims are typical. 2 is totally fine. Don't think that you simply need to add more because we're going to be more carefully scrutinizing you or more impressed if you have 3. So 2 is totally fine. Make sure you develop the idea as well. Some other important things, because this is essentially the umbrella to your grant, it's not simply an introduction. By the time we read the aims page, that one page, which should be incredibly clear, we should know exactly what it is that you're going after. In the biochemistry division, for example, we should know, is it more of a structural question? Is it a signaling question? Is it going to be answered using techniques in fluorescence? Is it going to be viewed based on immunoprecipitation and Western blotting? We should already have a sense of that. We should be able to anticipate what's coming in the rest of the grant. Okay, I think, so then it goes into significance and background. So notice very importantly, this first bulleted point, we should be able to understand what is the critical barrier to progress that you are addressing. This could be a technical challenge if you're, say, developing an assay. This could be the need for certain interdisciplinary technologies or the union of multiple different approaches. It could be a new reagent, which relates to the question that we were asked about characterization of a reagent or the application of a reagent to a biological question. Make sure you know what is already known, as you can see in the second bulleted point. So very simply, do your homework. When you give us a proposal, we can easily Google very simple ideas to know that, either you already have done this, don't repeat something you've already done and try to restage it as your OP, or someone has already done this and you are unfamiliar with what is out in the field already. And then make sure you identify gaps that you intend to fill through the successful completion of this project. So, for example, if you're going after a signaling pathway, what is the effect of having that new mechanistic insight? What does that then stage? And this has already been said, but don't promise to cure a disease. Obviously, any of us would love to do that, but have yet to do that. So this is not something we expect to come out of an OP. And again, this idea that you do not need to take a giant leap forward. So you can go to the next slide. Okay, for innovation. So again, this is a great opportunity to explain how you are leading the field forward in some way. And again, with this idea that it could be a new type of assay, it could be a new angle on a signaling pathway, it could be a new structure that you solve. One thing I might recommend in terms of formatting and making it easier for your committee to read and appreciate your innovation is consider using a bulleted list. Actually, very much like what you see on this slide. It makes it very easy to separate different ideas and to highlight concisely an important concept without needing to have a lot of prose, a lot of language to try and get to what is ultimately a punchline. So I often like writing my innovation sections as a bulleted list. Notice this can be relatively short, but should definitely be less than a page. There will likely be a lot of innovations in your ideas, but you don't need to point out every angle. Point out the biggest ones, okay? The meat of the proposal is then this next section on your approach and experimental design. Again, do your homework. Think about the overall strategy very carefully. Think about the methodologies and think about the analyses necessary to address the question. In fact, the most important point is that you should be reinforcing the aims from your specific aims page here. For example, you might use the language in order to address our hypothesis that whatever, we will do whatever, right? And that's a very clear way to connect the ideas from your aims page to what you will actually be doing. Keep in mind that not everything is going to be successful, so you should absolutely be thinking about alternative strategies. And just like has been pointed out, you certainly could show versions of schematics or possible data, whether that's borrowed from the literature or simulated. Just be very careful how you use these pieces of information. Cite something if you borrow it, make it very clear that this is not original data. And certainly if you simulate it, make sure we're aware of that as well. If you could go to the next slide. Oh, so then I can give you a couple other pieces of information. So make sure to have the literature cited. So you will be needing to look into the field. Yep, so at the top of this slide. Consider this a great opportunity to practice using a citation manager if you haven't already done so. So start using EndNote or Mendeley as a way to organize all this information. It'll certainly pay off in other forms later. In terms of the review process and the things that we're looking for, because this is your candidacy exam, we're really looking at the strength of your ideas, the feasibility of your ideas, your knowledge, and your ability to communicate. And we go into that in detail in all of these different bulleted points. It is important to point out that we're not looking for you to satisfy every one of these criteria absolutely, but please try to demonstrate the highest level that you can in terms of significance, innovation, approach, and your communication defending the proposal. In the approach part, I'll just emphasize, again, failure is inevitable. We all experience it. Almost nothing goes exactly according to plan. So it's really important that you think about mitigation strategies. What are the alternative approaches or the complementary approaches that can either replace something that fails or can bolster a claim so that you have multiple angles to effectively answer a question. And then on the last slide, just some general tips. So many of these have already been suggested, scheduling and planning well in advance. The next couple points really emphasize working with your peers and getting feedback. In fact, what is more often than not the case is that your peers are much tougher than your committee. And so in fact, you want this to be your experience, that you struggle through your practices. So it gives you a lot of opportunity to think very critically, not only about your proposal, but how you respond to questions. And then hopefully at that point, then having interactions with your committee will actually be fun. It'll be a just interesting discussion about scientific ideas. I certainly look forward to that when that happens from my perspective. And on that note, I would say, please expect that you will be saying, I don't know, right? It cannot be the case that you know everything in advance, you've thought through every contingency. It is totally okay to say, I don't know. Certainly that shouldn't be the answer all the time, but your committee will push you to get to the point of saying, I don't know. So this shouldn't surprise you if that happens. I already mentioned this. Please don't say you're going to cure a disease as part of your OP. Just below that, if your hypothesis happens to be incorrect, you'll still learn something. So make sure that you point out what can still be learned, even if you have a problem in solving the exact problem that you propose. One of the biggest challenges, this is about the fourth from the bottom. No, sorry, just above that. It says aims shouldn't be dependent on each other. So this is one of the biggest challenges in an NIH style grant and writing specific aims, that you want to have independent but interdependent aims as much as possible. What I mean by that is if aim 1 fails, you should still be able to do aim 2. However, it's the sum of the information from aims 1 and 2 that truly answer the question. So think very critically about this independent but interdependent relationship of your aims. So the next point has already been described. Make sure that you think critically about the information that you give to your committee, because everything that you provide to us, we can scrutinize. So think carefully about your imagery, your word choice, and so on. And then this last point can sometimes be a strategic one. So prepare backup slides for questions that you can anticipate. Sometimes one of your best strategies can be to plant questions. So that's not to say create obvious holes in your logic, but think about when you are proposing a technique, let's say based on my expertise, single molecule imaging. You can anticipate almost always the question, well, what are the effects of photobleaching? So make sure that you're ready to answer that kind of question. And it's often to your advantage to have thought about it already, because then you are prepared and you can demonstrate to your committee that you really are very well prepared. So I think those were the points I wanted to make, but I'm certainly delighted to take any questions if there are any out there.
Yeah, I don't know if anybody's joined, but make sure you put it in the Q&A section. We'll give a couple minutes for people to ask questions, and then.
Certainly, you can also reach out to me if you come up with the question at a later time, no problem.
Yeah, I guess nobody has said anything yet. So what we can do is at the end, if any questions have popped up, if you guys are still here, we can do that before we do like student-oriented questions. If not, I've led this for 3 years now, so I kind of know some things about the process. So I can do my best to answer. But yeah, okay, we'll move on to analytical. But thank you so much. It was great for your first time. And so now Dr. Julia Laskin's here.
Okay, hi. So I just joined, so I don't know what you've heard already. So I'll go through my spiel the way it is. Can you please go to the next slide? So again, this is my perspective. This is how I view the OP, and I think from what I've experienced so far, this is my finishing my third year here in the department. This pretty much applies pretty broadly across the analytical division. And the OP, I think the goal is for you to demonstrate that you can create an idea. You can be an independent scientist by exploring a new field, exploring literature. So you have to show that you can identify a topic, dive into the literature, evaluate where the field is, identify what are the gaps in this field, knowledge or technology gaps, and come up with an idea how that will address this gap. Okay, and then what you have to do then, the next step is to walk through this idea from the beginning to the end. So it's like, okay, so if I want to address this challenge, this is my idea and this is how I will do it, okay? So you have to design your own experiment. And of course, an important component of that is also to communicate this idea. And of course, you know, all of you write the proposal, and I think that's great kind of exercise in terms of just general scientific writing and proposal writing, and how do you put a proposal together, which will benefit you along like many different kind of career paths, but also communicate in a presentation. So when you present, or when you write, think about that, you know, you're presenting it to us, to your committee members. We're not there to try to fail you in any way, or, you know, to make you feel bad about yourself, but we're curious scientists, so we ask questions that a curious scientist would ask. So it's a friendly group, but the questions may be pretty difficult, you know, so. And, you know, if you step away from your, far enough from your topic of your PhD, we're pretty lenient at, you know, you know, not being able to address particular question. But if you demonstrate that you actually thought deeply about the topic and that you are actually standing firmly on your feet, I think that's what's on the ground. That's I think what's important. So you have to be in full control of the literature that you are in the field that you're presenting. So the passing rate is usually high, but again, you still have to take it seriously. There are situations where we ask for some additional materials for you to prepare. If you were not able to address some of the questions, you may be asked to prepare additional materials. That doesn't mean that you failed. You shouldn't be freaking out about that. You just have to kind of mine through that request and just, you know, deliver those materials to your committee members. They will evaluate your response. And, you know, usually I haven't seen people failing the test, but I have seen people the OP, but I've seen people being asked for additional information, for clarifying information. So don't just feel that, you know, it didn't go well if you're asked to provide some additional information. And again, so we'll be asking questions not to test you, but to understand your idea and the field. Usually we're not familiar with this field. So some of the questions will be naive and some of them will come to you just like, I didn't expect this kind of stuff, you know? So because some things, in particular, when you read some literature, everything becomes obvious to you. It may not be obvious to us. And so some of those simple questions, sometimes people kind of get thrown off by them. But for you to be successful, you have to make sure that you understand all of the aspects of your idea. So if you're proposing to use, I don't know, atomic force microscope to measure forces between DNA and protein, you have to know how this measurement is being done. So you have to understand the measurement really well. Or if you're saying, I'll be using a laser to excite my molecule, you need to know what kind of laser. Do you need to use a continuous laser or a pulsed laser? What kind of wavelength? And is this power of the laser sufficient to excite the molecule that you want to excite? So those kind of ideas where you just need to think through your points very carefully. And when you put things on the slides, you have to be able to defend everything that you put on your slides and in your proposal. You have to understand the advantages and limitations of different techniques very well. So just don't fall into the trap of piling up like a zillion different instruments to address a question without understanding how those instruments work. So let's go to the next slide. Okay, so where would I start? So I would go with like looking for ideas. I would go and see probably some review articles, and a very, very good source of review articles is Analytical Chemistry January issue. So just open that issue, look through perspective articles. They're not comprehensive, so they are relatively easy to kind of skim through for ideas. Annual reviews in analytical chemistry gives you some good ideas. There are some review articles in Analyst, Trends in Analytical Chemistry. If you want comprehensive reviews, you have chemical reviews and chemical society reviews, but this will be very long and sometimes it's hard to grasp an idea from them. And Accounts of Chemical Research also publishes some really cool articles in different fields, so you can get some ideas from there. And so again, finding a topic, identifying gaps in a particular area, proposing a solution, and making sure this has not been done before, and being able to articulate what's new in your idea. I think those are your key components of your OP. So one thing that and maybe it's my personal perspective, we don't limit the topic areas, but I think that in particular for analytical chemistry, just focus on chemistry and analytical chemistry as much as you can in terms of your solutions, right? Because this will benefit you as well, not just to allow you to pass the exam, but people sometimes go out of their way into completely different fields, which is also cool, I think. But I think for your own benefit, chemistry and analytical chemistry is what you want to focus on. So if you select your topic, as I said, if you select your topic far enough from your area of research, then this is basically a high novelty, and you get more freedom in, kind of not being able to address all the challenges in particular in that particular field. If you get closer to your PhD topic, it's considered lower novelty, and then there will be a lot more scrutiny on what you're proposing. So and we do encourage you to step away from your area of expertise, but I always encourage people to build on their existing areas of expertise from your undergraduate research, from some of your maybe course materials that you enjoyed. So just build on your existing expertise. Don't start completely from scratch. That's what I would recommend. Okay, let's go to the next slide. So here is a structure of the written proposal. So I don't want to read through everything, but just very quickly, you state your objectives. So those are kind of a guidelines. You'll have those in your handout, so you can go through those. You have to articulate background and significant, what's important, why is it important, what are the gaps, why do they still exist? Why they haven't been addressed by others, in your opinion? And what is that you're trying to address with your proposal? Specific aims is always a very important part of any proposal, so you just keep it brief, but those have to be like, those have to articulate what specifically you're proposing in your OP. So for generally, like just as a general rule of thumb, it's good to have 3 specific aims. And it's better that, I think it's in a different slide though, but it's better, no, it's in this slide. So it's better that if they are not sequential, so that if one of your specific aims fails, then you cannot go to the second one. So we don't scrutinize that with the OP, but in general for a proposal, if you're putting a proposal, if all of your specific aims are dependent on the success of specific aim 1, then your risk is really high. What if that specific aim 1 fails, then everything fails, so you will not get your proposal funded. Again, if you can put aims such that are not sequential, that's great. We don't really scrutinize that at this stage. I'm sort of bring this up as just a good idea for generally writing a proposal. And so the approach, you have to explain how you address your aims and how you solve them, and summary, what's the outcome of your proposal, and references. So, okay, so let's move. Do I have another slide? I think I do. Or is this the last one? Yeah, and so I guess that's the important component too. How do you present your OP exam? So you prepare for about 20 to 30-minute presentation without questions, and you are have to be ready to be interrupted. Use figures from the literature to support your data. Don't make up data. If you want to simulate something by yourself, please do so, but also indicate that this is your simulation. But don't try to make up data. Well, just general, for presentation purposes, make sure you use fonts that are visible. We're older people, so be mindful of us, okay? We don't have as good of a vision as you do. So, and we get frustrated when we cannot see fonts. So, just be mindful of us, and be ready to defend everything you show on the slide. Have a bunch of backup slides if you have any questions that are being asked, that backup slides can help you address them. Again, with your experiments, you have to articulate the novelty of your proposal. You have to explain the experimental approach, and what is that you have to do first, what comes next. So just think about the sequence of events, and explain what will be the outcome of your proposed work, and be prepared to give a brief research presentation. Sometimes we'll ask for it, sometimes we don't, but just put some slides together about your own research. You may be asked at the end of your presentation to talk about. So with that, if you guys have any questions, so this will be all in your handouts, so you can read through those. But if you have any questions, please, I'm happy to answer them. Does NSF have a template for proper proposal style? I don't think they have a template, but they have a list, what has to be in a proposal. So if your PI is willing to give you an example of an NSF proposal or NIH proposal, it's always good to have as a guideline. Some of them are short, so some of the NIH proposals are just like 6 pages narrative, so it will give you an idea of how the proposal is written in general. Each agency has very different format of their proposals, or quite different. So it's not, it's good you can pull up from NSF guidelines for proposals. You can pull up a list of things that they require you to include in a proposal. So there's like 12, I think, different bullet points, and they do explain which what is what in that in their guidelines. Anybody else with questions? All good?
I guess we can move on to if anybody has any general questions, and we can wait for like 5-ish minutes with the faculty, and then we can let you guys go, and then have any students ask us any like questions that about the process, or unfiltered responses from people who've gone through it. So any general questions? Anybody want advice? Anything like that? And we will send all of this. When I was doing my OP, I think I used advice from every single person who presented at the OP help session. Yeah. Wait a couple more minutes. Okay, I mean, if nobody else has questions for the faculty, we can let you guys go. And then Danielle and I can sit here and take any questions about the experience and give some advice and stuff. So thank you all of you again for joining us. It's really helpful every year.
Okay, good luck, everyone.
Good luck.
Bye.
Yeah, best of luck.